Thursday, 1 to 3 p.m. And also Friday, which I believe 3 to 5 p.m. Check Piazza. So the way this works, it seems you cannot see what I shared. Let me just check. What is happening? Oh, yeah. Sorry, wait. Let me I'll just be using the iPad for audio, because that has worked before. This is strange, right? So where's my screen sharing still not working? That is strange. Do not work. Yeah, so question for you guys. Can you guys see slides or no? Not at all. Thumbs down if you can. Something. Oh. Yeah, I'm not sure what is. Huh? Okay. Yeah, let me just get out and rejoin from my. That is strange. I'll share screen. This should work. Yep. Okay. Yeah, sorry about the delay. So yeah, assignment Q&A, the way it works is you submit a Google form question in which you feel free to include what you have tried. So this information you may not be able to share in a Piazza public forum, or if we hold, let's say, an online Q&A, you won't be able to just blast it out in a group, but the tutors will see. And then in the session, the tutors will basically collect the union of questions and also monitor questions that come in real time in the Google form response, so that they can sort of give hints that help you condition on the information you provide them, including the private information. So there will be 2 tutors per session. So one is Alex and Charmaine, the other one is Alex and Josh, I believe. And so there is some capacity to help people who come into the room and also online. Hope you find that useful. Right, so today's plan is we talk about PCA briefly, which I'm assuming that you've either recently learned or recently refreshed on the vanilla version of PCA. We talk about the probabilistic formulation of PCA as an instance of applying what we have learned before. And we were going to gloss over details, but just to give you a idea about, oh, here is something that uses what we learned before, especially conditional Gaussians. And then we'll be spending a fair bit of time on autoencoders. We'll then talk about recommender systems, which so far, or the recommender system that has been developing in the last 15 years have depend a lot on dimensionality reduction. And we'll talk about autoencoders in recommender systems as well. In last year's class, the autoencoder for recommender systems was homework 2. This year it looks like we are going to change the question, but but it's still a good thing to know about. So the content of this particular session is mostly from the PRML book. There's a section that we won't cover today. We'll see about after the kernel session. Again, this was last year's homework, and people do like this topic, kernel PCA. So I'll leave you to read it after next week. The recommender system content is coming from Kevin Murphy's probabilistic ML book that has a link in the course website. It's also free, the new version. So here is a brief recap of PCA. Our data is still x1 through xn. Each of them, think of them as d-dimensional. And an important quantity in PCA is the centered, basically, covariance matrix of the data after we have centered the data. When we talk about covariance matrix of the data, we always assume the main mean is being subtracted. So when you see PCA being described in different places, make sure you do the mental check about removing the mean. If you just call some covariance function, then so whether we are doing essentially the covariance of mean removed or just the expectation of x squared as vector. So there are two different formulations of PCA as presented in the Bishop book. One is called maximum variance projection. So if I wanted to reduce the dimensionality from d dimensions to, so each of these xi's are d, or want to reduce from d to m dimensions, how do I do it so that the variance of the remaining is maximum? So it turns out that we do so by finding the eigenvalues ui and eigenvectors lambda I of the covariance matrix, and then we just project x down to these ui's, right? And for the covariance matrix is positive semi-definite, and the ui's, the different u's, they form an orthonormal basis, meaning each of the u's, ui transpose ui is 1, and then ui transpose uj, the inner product of a different eigenvector is 0. They're orthogonal to each other. And we can sort the lambda i's from the largest to the smallest. They're all positive or non-negative. Right? And that's how we number the lambdas and u's for the whole next section of the content. Right. So equivalently, there's the minimum error formulation, where the error after projecting down to m dimensions can be written as follows. Basically, we sum over the remaining components from n plus 1 to d, and then sum over the data set from n goes 1 to big N. And the minimum error is shown to be basically the last n plus 1 through d components, right? And they sum up to the smallest eigenvector values. Right. All right. And the general, I guess, geometric picture for PCA is like this, right? So since we can most easily draw in 2 dimensions, if the data covariance contours of the data covariance matrix is this slanted ellipse in, let's say, 2D, PCA tries to find the principal dimensions first for maximizing the projective variance, and then find another direction that's orthogonal to it, right? Yeah, when in 3D, you then imagine it's sort of a rugby ball, since we're in Australia, that are somehow rotated in space. So you may ask, right, so this next section of the book say, oh, let's formulate this probabilistically. So what does that mean, right? So now we call the latent dimensions, or the principal component dimensions Z, that are distributed according to standard normal, and they are uncorrelated to each other. So basically, Z is in M dimensions, smaller dimensions. X is in D dimensions. Z are independent of each other. They're normally distributed with univariance. Probability of X conditioned on Z is a linear transform in Z. Basically, it has a mean component. And this will be the center of X. And then W times Z is linear transformation. And we assume that the mapping has its own additional noise term. That's a scale version of the identity matrix, right? And this W matrix is now D by M. So if we assume D is larger, M is smaller, so D by M. So this is W matrix times Z, which is the shorter vector. This is the 1 by M matrix, and the result is a long vector X, right? So you may say, well, this equation 12.32 looks rather familiar. That's because we've been staring at this marginal and conditional Gaussians a few times by now. But basically, well, we specify a Gaussian variable and then a conditional distribution of a linear transformation of the Gaussian variable. So this is exactly what it is, except they're just called different things. So if we take this content in chapter 2, and then we call substitute the X as Z and Y as X, then we get almost exactly that. And the isotropic Gaussian identity variance is actually a special case. It is just a bit of symbol manipulation, a bit confusing. So you may ask, what does this buy us? Right? So, well, hinted by this conditional Gaussian blurb, we can now try and infer, let's say, well, P of Z given X using Bayes' rule. We could also, for P of X, and so on. And this is what the book does in the next page. It did it sort of 2 ways. We could simply plug in the formulas from chapter 2. The book reasoned it sort of from scratch. So if X conditioned on Z is this W times Z plus U, where Z is zero mean, then the mean of X is mu. And then the covariance of X is derived by writing X as a linear transform of Z plus mu plus a noise term. And then we can compute the covariance of this as W transpose plus the variance term of X itself. Right. So note that this covariance of X, because of the X dimensionality, is for sure d by d. So imagine we're operating in some huge dimensional space in the tens of thousands or even millions or more. So modeling a Gaussian in the super high dimensional space is not great because like computing the inverse of C, which is needed by evaluating when you evaluate the Gaussian distribution. So it needs order of d cubed computation. So this is, I feel the numerical aspect and computational aspects of doing these linear algebra operations has not received enough attention in undergrad curriculums. But rule of thumb, after being exposed to this a number of times, rule of thumb is that matrix multiplies, it's easy for us to sort of intuitively figure out how many multiplication of your operations you need. For inverses, matrix inverses, it's the rule of thumb is it's n cubed for a matrix of n by n. And for computing eigenvectors and eigenvalues of a matrix, when you don't need all the eigenvectors and values, it's cheaper than that. Let's leave it at that for now. So this next bit just does what I just said, spells out how we try and derive C. And then the book applies a trick on what's called matrix inversion identity to compute the inverse of C actually more cheaply. Basically, it does so by inverting an n by n matrix, which is a lot smaller, rather than a d by d matrix. So this is order of n cubed. So as we know in a lot of real world cases, the variance or the number of significant PC dimensions is small compared to the whole data sets. So this is valuable. And the core, so as we said, we're going to use Bayes' rule to invert the conditional. So P of Z given X can be computed involving just the M's and not the original covariance matrix. So there is some let's say, representational advantage here. If given X, we want to compute the latent dimensions, that we could do this. Right? Because we've talked about Gaussian mixture models and the discrete latent variable models, right? So right now we have essentially a linear Gaussian model where the latent variable is continuous. Now let's just write out the log likelihood of X given the parameters of the PCA model or the probabilistic PCA model, which two places, 2 pages ago, we can write that the parameters for this model is Z doesn't have any parameters, zero mean identity variance. So the parameters are W as a matrix, mu as a vector, and then sigma squares, which is a scalar. Because this is the model, and then we can specify parameters. The next question is, how do you estimate it from data? Right? In PCA, we start from a pile of data, basically the X as a matrix, or n rows of X vectors. We would like to recover the PC dimensions. So what do we do here? So in terms of these three parameters, if we think about them in the PCA, in the like non-probabilistic PCA terms, this is the rotation matrix. U. Mu is just data mean. Something new, and this is another noise term, additional noise term. So the intuition here is if we apply the thinking from vanilla PCA, like obtaining the rotation matrix will also lead us to the eigenvalues. So we start by writing the incomplete data log likelihood, which we just write it using, in the last slide, we said, well, from these three parameters, now x, or p of x, p of z is, sorry, it was just p of x without the conditional. P of x is simply normal of mu and c. So we do that by simply expand the expression, and we get this data likelihood in mu and c. And we know that c has a closed form expression from these parameters. You may ask, oh, okay, what has changed between the discrete and continuous latent variable model? So this expression doesn't look too bad. We can actually differentiate and find the maximal likelihood estimate. So what we're saying here is these are linear Gaussian models. Yeah, actually model is a very overloaded word. So if we're looking at latent variable models, which the relationship are linear Gaussian, the incomplete data likelihood is actually tractable. So it is the Gaussian mixture models is one of the simpler cases where we really see a benefit of the EM algorithm and trying to solve for estimated probabilities for X and Z differently and doing the E step and the M step. So it turns out that in the Bishop book, because the probability PCA is an approach that Mike Tipping and Chris Bishop, they proposed themselves concurrently with others, they did devote a fair amount of space to it. They say they have shown, and this discovery was done, I think, in the turn of the century, around 1999, not that long ago. So every solution to the maximal likelihood problem specified here can be expressed like this, right? So the rotation matrix restricted to m dimensions can be expressed like this. So basically, U of m is the matrix consisting of the first m eigenvectors. L of m is the diagonal matrix with the first m eigenvalues, subtracting the noise, and then multiplied by any arbitrary rotation matrix R. And the maximum likelihood estimate for the sigma term is simply the sum of the remaining eigenvalues. The book has an exercise for us to get to the bottom of this, but for the purpose of this particular section, I feel that the value for this exposure is not necessarily in deriving this, but basically the language we've acquired so far allow us to think about PCA in a different way. So you say, well, it's a latent variable model. How about EM? Turns out we can do EM too. Again, sparing ourselves the details. Basically, EM, we wanted to compute the expected likelihood under the conditional probability distribution of the complete data distribution. And the expression, I'm not going to write it out there. The book has it. And then the E step computes the expectation of the sufficient statistics of Gaussians, basically each of the latent dimensions and its outer product. And then in the M step, you could build a new, like an updated round of W, estimates of W and sigma squares from the E step. You may ask, right, so why do we need EM if we can already have analytical expressions that solves maximum likelihood? The question is, so the MLE for W and sigma square requires the full covariance matrix and also the first M eigenvalue vectors. Right, but the argument put forth in the book is that during EM, right, we only need this matrix M. So computing as itself is d squared. When the dimensionality reduction is significant, then this M matrix is significantly smaller. So there are computational savings. All right. So this is basically a very quick overview of probabilistic PCA to essentially tell ourselves we have all the knowledge to get to the bottom of this, despite we don't in this lecture. And there are different ways of thinking about something familiar such as PCA. And in probabilistic PCA, we cover the rotation dimensions, but we also estimate this additional noise vector. Okay, so this is still, linear dimensionality reduction. So moving on, we talked about neural networks on Monday. So let's talk about autoencoders, which is a specific type of neural networks. In the book, chapter 12, there's this picture called two-layer associative neural nets. It's called associative because it's trained to map input vectors onto themselves by minimization of the sum of squares error. So this, at the first sight, might seem like a strange concept, right? What am I doing? I give it a bunch of input vector x, and then I want the output to just copy x. Turns out this idea can take us a long way, right? As you will see. So the key is right. The key insight is that this latent this latent dimension, latent representation, it hopefully captures. So when again they have like the corresponding, the input is d dimensions, then and we have m latent dimensions. So hopefully the latent dimension are capturing the core information in the input, so that you might want to, it can do one of two things. One is to do compression, meaning when we have fewer latent dimensions than the input, or it can do nonlinear feature mapping, where the number of latent dimensions is essentially infinite. And there are bias terms too, but we just omit it. So let me pause here. So since we're still not quite out of the PCA round, and answer the two questions. So what are the motivation of using probabilistic PCA in general? In fact, even in regular PCA, you always have soft assignments to different principal components, because so it's not that, right? So in this expression, so this is assignment of two different components. And the reason we would like to express this in probabilistic PCA is, one reason spelled out in the book is when we don't want to compute S, or don't want to invert or compute all the eigenvectors of the data covariance matrix. So that's a computational reason. In terms of representational reason, the book spelled out a whole bunch in the beginning of 12.2. If you don't want to read the rest of the section, they had a fairly good bullet list, one of which is to account for missing data. And if you like EM algorithm, it allows you to do EM with computational savings. And then the claim is that PCA itself doesn't lend to a likelihood function or a density function. Now that we can explicitly express the densities of x given z, x, and z given x, we can compare and contrast this to other density models, and connect to them and extend them if you're doing machine learning research. And Qinyu asks, can we say EM gives us the generative model about X and Z, but MLE only cares about X? I would say no, because the model actually is spelled out in this current slide that we're on. It is generative in the sense that if we know the model, which is in this green box, it starts with Z, and we can get X from Z. In MLE, despite we solve for the parameter W mu and sigma squares, essentially we can derive Z, right? Well, this one is a bit of a strange one. The model for Z is actually fixed, so we don't quite need to analyze it. And I hope that helps. Seems yes. Okay. If not, shout at me. Right. So associative networks, as we can see, we started talking about autoencoders. The claim is that we haven't. This is really PCA we're talking about if these mappings are linear. To make that point, right? So the book did make the same point. If we're minimizing the square error between the output, basically y of x comma w is the output here. We put x through these bottleneck nodes, and then reconstruct a y. If we do this, if all the hidden units have linear activation functions, then it can be shown that this error function has a unique global minimum. And at this minimum, the network performs onto the m-dimensional subspace, which is spanned by the first m principal components of the data. All right, yes, we're still doing PCA. That's the vector of the weights which lead into the hidden units of these from a basis set, which spans the principal subspace. It doesn't have to be the orthonormal principal eigenvectors. It could be any arbitrary rotation of them. Remember the R term a few slides ago. Right, the next section of the book makes exactly this this point. Don't need to be normalized. The result is unsurprising, since both the PCA and neural network are using linear dimensionality reduction and a minimizing of some square error functions. So this is another connection from the various things we have learned. And I liked making exam questions out of this. This was one actual question from last year's exam on Watto. Obviously, I'm showing it to you here, and this year you're not going to get the same question. It actually takes some crafting to sort of precisely formulate this, right? So consider an autoencoder with 4 input dimensions, with 2 hidden units and 4 output. Okay, exactly an autoencoder. So 4 input. This is use, and then 4 output, right? So these are x primes, x, and they're all fully connected. I'm not going to draw that. Yeah, so just something like this. And then, okay, I'm giving you a training data of 10,000 points in 4 dimensions, and I already centered them, so don't bother that. And we know of a S matrix, which should be 4 by 4, right? And now I've also given you the eigenvectors, and the notations are V like this. And moreover, we've given ourselves, we transpose basically the row vectors of V, right? Now, if I set basically the weights of this linear network to be V, and essentially the first 2 rows of V transpose, and essentially let gradient descent loose on this, what will happen? So as you can see, right, because we just talked about it, you're like, this is PCA, right? The network should stick to the PCA solution because it's the global minimum. Let's read the options, right? If we aim to minimize the square error between x and x prime, with a commonly used L2 regularizer, the weights will remain unchanged. As we just said, well, PCA is the global minimum. We set the weights to a PC vector, then it should be okay. Turns out this is not true, right? Because the PCA objective did not include L2 regularizer, so no for that one. Option B, we skip. Right, and then C states x prime is the minimum error reconstruction of x given this network structure. So that's true. That's one way to formulate PCA. D, if we perform gradient descent on the square difference between x and x prime, the weights will stay there. That is true. So the shape of the error function in the weight space here, there is no unique global minimum, right? But all minimums are up to rotation. So remember we showed a picture of like a wine bottle, right? Something like this. So if there's the weight space, W1, W2, we have a lot more weights, but we can't draw in high dimensions. So if this is our V, eigenvector of first 2 vectors, something like that, then there is a whole connected region that like V times some rotation matrix I is also going to have the same reconstruction error or square error. But I can't quite ask you all of that in a multiple choice question. Therefore, right, these are all under the hood. Right, the last one is another trick one. I said the variance of x prime is maximized given this network structure. So let me pause and ask guys whether this is true and why. Takers, true or false?
Not entirely sure, but I think it is false.
Yep. Oh, so okay, Jinhong, do you want to elaborate why?
What I'm thinking is PCA actually maximize the compressed version. So it tried to maximize the variance of the compressed version of the input X, but the X prime is actually the reconstructed version of X. So I think if it's saying that, I believe you denote the compressed version of X as U, which is the bottleneck layer of the autoencoder, then the statements will be correct. But I don't think the variance of the reconstructed X prime will be maximized with autoencoders.
Say, if this is changed to U, then it's correct. Actually, there's another trick, right? It's incorrect. Right. I should probably have worded this a bit better because variance itself on the vector is not quite defined. But if we say what, like determinant of the covariance matrix and so on, then it's kind of like the covariance, right? The determinant or trace of covariance matrix of X prime and U are the same thing. And there's another thing. There is no strict constraint that this the wave vectors, if we express them in terms of V, has to be orthonormal. Meaning I can just multiply an arbitrary constant on the input weights. And then the magnitude of, say, U, and that will be a lot bigger. So there is no actually strict norm constraint on V either. That's another part that's sort of underspecified if we just think of this as PCA. Anyway, this question was somewhat tricky last year. So now that I've showed it to you, I also can't use it in the quiz. But I hope you like understood this by now. So what do we do? Right. So what does this? So right now we've still been doing PCA, but just drawing them as neural networks. What if we add another layer? And what if this layer is nonlinear units? Of course, then the mapping between, so in here we're mapping from X to some Z, let's say, and then to X again, maybe X prime. So from what we learned on Monday, if we have a two-layer network, so there's two layers, and there are suitable nonlinearity in there, so we can essentially map anything, like basically from the universal approximation property of neural nets, we can map any function, that we can write as Z equals f of x. Any is a little bit loose, like you have to be continuous, like Lipschitz and so on and so forth. Right, and yeah, the output is the same. Essentially, we can then map any function x prime of g of z, right? So having powerful representations makes us feel good, or yeah, allows us to do a lot of different things. So if we're reducing the dimensionality, here's a picture, right? Assuming the original X is in 3-dimensional space, Z is in 2-dimensional space. We first perform a nonlinear mapping to go from 3 to 2 dimensions. Basically, yeah, 3 dimensions is a high-dimensional, not quite cube, but like the entire space gets smashed into the flat 2 dimensions non-linearly, and then it gets expanded back to 3 dimensions, but not as a flat plane because it's not a linear transform. It could be any curved surface. So what we are learning here is then sort of a subspace, curved subspace in 3 dimensions that are somewhat arbitrary. If I have, let's say, an arbitrary shape in the original 3 dimensions, I'm going to attempt to draw a donut, although my drawing of donut is not very good. Yeah, let's say, then we can essentially squish it. Yeah, like these nonlinear mapping allows us to learn these irregular 3-dimensional shapes. So that seemed to be a good thing, right? And then the next, we just went from 1 to 2 layers, and we claim that it's a good thing. The next chunk of content, we're going to try and claim that having more than 2 layers seem to be a good thing. We already know that from the last few years that having more layers is empirically a good thing. Here's a little more sort of fairly imprecise, but hopefully gives you the right why deeper is better. So it started in this pair of papers that I could find in the literature. So, right. So for the deep learning community, a lot of people sort of stopped tracing the intellectual lineage when they reached the Spangio and Delano paper in 2011, where they explained why deep architecture is more expressive. So in the so there's paper by Hastad in 1986 and also by Andrew Yao in 1985. They showed that like a d-bit parity function of depth 2 it needs to have like exponential size. So if we have essentially 0, 1 outputs and we want to check, so there are certain class, so parity check function are essentially telling us whether the number of ones in the input vector is even or not, right? And it's being used a lot in practice, right? In communications, in different sorts of encodings. If you ever typed into a credit card number on the web form wrong, it will immediately tell you that it's wrong. That's because there are parity and other checks that are built in. So simple things like parity check takes exponential number of units to do because it kind of relies on every single input, and it's not a local function like what your convolutional neural networks do. So that's what Yao and Hastad showed. And the designers of deep neural network used this very theoretical result, right? So this Yao's paper was in FOCS. Yeah, I think I forgot which one is. Hastad is in either FOCS or SODA. So, but these are the top theoretical computer science venues. And after more than 15 years, it made it into the deep learning literature. So there's a good reason to study theoretical computer science, as because your results might be part of the next wave of machine learning revolution. Right. So the statement here is functions that can be compactly represented by depth k architecture might require exponential number of elements if we just reduce the number of layers by 1. And the rest, a lot of you know already. So Benju and others basically devised deep architectures that are convnets of images that has other operations built in to learn essentially different kind of correlation structures in images. There are other tricks about convnets, for example, sharing the filter structure across the image and so on. We're not going to go into that just yet. So the challenge of just adding more layers and just making networks deeper and deeper isn't necessarily a good thing in practice. As we said, well, deep architectures have a lot of local minimum and plateaus. The optimization landscape is rather complex. On Monday, we saw a small sample of those, and there are a super exponential number of global minimums too. So it's hard. It's been not like how to initialize the random weights well has been a challenge, and deep networks or large networks tend to overfit. That was the wisdom of the 90s. So what went into what's called the current wave of deep learning, whatever you call it, deep learning hype or deep learning revolution. Part of it is computation. Part of it is the let's say improvement in architectures and realizing that deeper networks are more expressive. Another part are many of these little practical tricks that avoid the pitfalls of neural network training and getting stuck and overfit and so on. So up until the early 2000s, the wisdom has been, 1 to 2 hidden layers seem to perform well because we don't know how to deal with deeper layers, how to train them well, right? In 2006, the early days of deep learning, the wisdom was, unsupervised pre-training on deeper autoencoders seem to be doing well, meaning if I have an image which is trained to reproduce itself on MNIST, and then I cut half of the autoencoder off and then use the representation in ML. That has not been the case in the last 5 to 8 years. But that's how deep learning, autoencoder is how deep learning was, how deep learning restarted itself, right? Yeah, of course, in practice, you now have these systems that don't just have neural network layers, but also have things like pooling and app convolution and so on, right? Not gonna delve into that. So these are the practice. Let's look a little more on autoencoders and deeper autoencoders and the practical tricks. Right. So if we formally stated, autoencoder is trained to encode the input X into some representation C of X so that the input can be reconstructed from that representation. So C of X in the book is called the bottleneck hidden layer because it's assumed to be smaller than X, although in practice, it doesn't have to, right? In lots of, like we also talked about over-parameterized models, in that case, like a lot of the middle layers are bigger than the input, and it's okay. Right, with one, this is more of a recap. If we only have one linear hidden layer, then we are learning the first principal components of the data. If the hidden layer is nonlinear, then the autoencoder behaves differently from PCA. So it doesn't treat the input data as a multi-dimensional Gaussian that look like a high-dimensional rugby ball sitting in some space anymore. Now we can have multi-model data, meaning when we have nonlinear mappings, arbitrary mappings, we could think about Gaussian mixture models, right? So in high dimensions, we could have a rugby ball sitting somewhere, a tennis ball sitting somewhere else, and we will be able to map the even disconnected geometry into a lower dimensional space, which is attractive. Or maybe we have, say, a donut or like a curved surface, and we'll be able to map them in low dimensional space. So for example, words like manifold learning has been popular for a number of years that are essentially concerned with learning like complex local connected structures and representing them. Okay, so the error function for autoencoder, or the loss function for autoencoder is generally like this. If our reconstruction function or the output layer is f, then reconstructing C of x should approximate the original input x, and then we just put the loss term, square error, or whichever. So we have denoted f of C of x as the reconstruction. We could also hope to express this probabilistically. There are many different formulations, but in general, you can think of the probabilistic formulation of looking at the distribution x given the latent representation C of x. And now we wanted to minimize the negative log likelihood. It is sort of a mouthful to say, but it's equivalent to saying maximizing the log likelihood of x given C of x. Right, again, if this conditional distribution is Gaussian, then it's equivalent to square error. We saw this a few times. Yeah, if the input are binary or have binomial probabilities, we get back cross entropy loss terms that we also saw a few times. So since we can do one mapping from x to C of x, why not going deep, right? So you can have multiple autoencoder layers. We first stack them, and then we stack the inverse function in the other order. Then we have a deep autoencoder. Sometimes they are called stacking autoencoder. There has been many names for these. Another nice thing about autoencoders is that we can interpret what's happening in each layer. And these are some of the early, this has contributed to people's understanding in the last 15 years of what these deep networks are doing. So remember each of the neuron weights, like we can essentially change the input so that it maximizes the inner product of the input with the weights. So for each neuron, we can essentially find the input that activates it most, and this is what these pictures are for. If you have taken computer vision, you will have seen, I guess, fancier versions of that probably, where the lower layers of ConvNet learn convolutional neural network tend to learn local structures such as edges in different directions and strengths. And then we learn simple combinations of these edges that are form simple local shapes. You can already sort of parse out part of the nose and the eye, and so on. And then the combinations of these intermediate local structures into something that makes more sense. So I think about 10 years ago, the initial Google Brain team, they had a T-shirt that says "Learning cat faces since 2010." That refers essentially to this. When they show up in conferences, you see like everyone in Google Brain sort of wearing the same uniform. All right. So also this is the early about, yeah, from between 2006 and 2010, latent features in autoencoders are shown to capture high-level patterns, and a lot of them are then reused for supervised learning tasks. More interestingly, right, in contrast to feed-forward neural networks, these autoencoder features are said to be constructed in an unsupervised fashion. Unsupervised, that's interesting. Right. Right. The premise is that I can just then cut the second half of the autoencoder off, and then just train another logistic regression for some, say, image classification task, and it will do well. This has indeed been true, right? So there are several takeaways for this. One is, how do I call it? Task transfer. Meaning things, networks that are trained for one task can potentially be fine-tuned or retrained for another task pretty easily. This has stood the test of time. It has been shown in computer vision, natural language processing, and other domains that you can do this. The other takeaway that is very much still relevant now and in the practice of neural network is self-supervision, if I can call it that, especially in the practice of large language models. Language models are trained to predict the word from other word before it or surrounding it. So it's not exactly unsupervised, but it's just the supervision signal is embedded in the data that we train on. In fact, this morning I was in a local research seminar. Let me see if I can dig up a pointer. Right, so we've been discussing the paper that started essentially the self-supervision and task transfer in 2016 for natural language, because before that it was all done for computer vision and people were wondering whether it can be done in NLP. Turns out it can. The author, one of the authors is Australian, Jeremy Howard. It's very interesting. Okay, I'll post that pointer to the teams afterwards. Right. So we talked about the difficulty in initialization. And on Monday, we've got under the hood and told you why initialization could be difficult. That's because of the vanishing and exploding gradients problem, or saturation problem. So as shown on the right, so sigmoid functions tend to, they saturate on either ends. We want to be in the middle, which is sweet spot. ReLU are essentially dead on the left-hand side. If you have other activation functions, they have similar problems. And we also need these functions that saturate because the universal approximation property relies on the function being our Lipschitz. So they need to be, they usually need to be somewhat, like the growth need to be bounded. Right. So this this well-known trick in neural network training proposed by Xavier Golorot. They're either called Xavier initialization or Golorot initialization. So it's quite simple, right? If we assume our input is each input is ID Gaussian, and assume they are not correlated to each other, which is not true, but let's also assume that our weights are Gaussian, and we compute the activation as basically a linear combination, the inner product of both. We can compute the variance of Z, and we obtain essentially m times sigma squares, essentially the number of neurons times the variance of inherent variance of the weight magnitude. So that's a helpful insight we can use, meaning that if we want, like if the variance Z is too large, we get into these saturation regions. So we want to modulate the variance of Z so that it's not too much. Therefore, we set sigma squares to 1 over square root of m, so that when we initialize the weights, we modulate their variance based on how many neurons we have, so that our output is roughly, say, have unit variance. And hopefully that means they stay around 0 and don't go too far away. So if we initialize properly, then this will lead to nice back-propagated signals. Because once a gradient hits 0, you can't really recover from it by doing backpropagation anyway, because when the gradient is 0, it doesn't move, the gradient just stays 0. Yeah, so using ReLU activation also helps in practice if we're in this linear region. So these are some of a small like sample of practical tips of the deep learning age. So let's talk a little more on autoencoder and entertain ourselves with some images before we dive into recommender systems. Right, so we recap from 3 minutes ago. We would like to minimize negative log likelihood, right, of getting back x given the compressed or the bottleneck hidden layer of C of x. The title of this slide is called denoising autoencoder. That's because of this ingenious use of autoencoder, saying that, in a lot of cases, I have noise in my data. Think about pictures or satellite pictures in OH. And turns out that if I have a decent noise model, I can just pump corrupted data into the autoencoder as input, and then use the clean X as the output, train it, and then this pipeline should just clean up my data for me. And this was indeed what happens. If you do this with images, this slide shows if you have images with Gaussian noise added. Like here are the generated noisy data and the clean version. These are really classic image processing, test images in the 90s, before the age of lots of pictures on the internet. Each of these pictures have an interesting story that I will spare you with. But anyway, the first image called Lena, lady in front of mirror, you can add noise to her. There's lots of research being done on image denoising and image compression on her and other of these images. And then if we just pump it through what's called the stacked denoising autoencoder that we saw last slide, we get a picture back that looks pretty decent. At least a lot better than the noise version, right? And this was proposed by then a graduate student in the University of Science and Technology in China and published in NeurIPS. It has had at least thousands of citations since I last looked. And if you look at the research paper, right, so this, I argue, right, reading a research paper is one of the basic skills to do advanced machine learning and do research, because a lot of you will be looking for research projects. You can basically ask yourself, okay, we know stack autoencoder and roughly what it looks like. In denoising autoencoder, the objective function is this, right? So the y of x, the model spec is specified here, and the loss function is specified here, whereas the learning process is encoded in here, where it just says, well, given all the parameters, I just wanted to minimize the loss function and get me the best parameters. And then what happens is this other twist on top, right? So they're called stacked and sparse denoising autoencoders. If we examine the loss function here, the first term is essentially the same thing with 1/n added to it for good reasons. And then there are two additional terms. One is the KL term, the other one is the familiar L2 regularization term. So I'm not gonna go through what this is. But then you just have to go in and examine these, which one is sparse and what does it do. And there's some evaluation out there. So reading a research paper, if you're new to this business, I think the quickest way is for you to find these key paths and then dissect them to get the key idea. Of course, if you're completely new to the problem area, first read the introduction to get to know what problem they're solving, and then latch on to the technical gist. And if you're trying to reproduce it and then come back to it the third or fourth time to understand the evaluation or all the other details that's needed. Right, so how does this work, right? So we essentially WAC autoencoder against images, we can resize an image as well. And this outperforms, let's say, the conventional resizing, which is by cubic interpolation. If we only have a small, well, during training, we have large images, we resize them down and then train it. And then in prediction time, we take a thumbnail image and then ask the model to essentially imagine the additional details in the high resolution image. And it does so pretty decently. Right? So this line of work have essentially generated lots of excitement in the image processing graphics community, right? You can, for example, in-paint the image. If your image is somehow corrupted with lots of text, this is from the same paper, you can undo it because the text, traditional denoising assumes you know a noise model. With these things like overlay text, it's hard to have an analytical noise model, but with autoencoders, you can still sort of remove it, which is rather neat. If you see, for example, an image meme that you like, you can put it through this and then put a different text on top, right? And this is the Free the Bird demo, where when you have irregular noise, if you take a picture but there is a light pole in front of some, like a keypad of the picture, you can remove it. In this case, it's even more extreme. I have a parrot in a cage. The in-painting model can actually remove the cage for me. That's pretty cool. So that's the entertainment on image processing, and which I hope also serves as a sort of a culture session on how we can frame a diverse set of problems into the kind of models that are kind of dry looking. Right, now let's talk about recommender systems. We'll introduce recommender systems in a few slides, and then we'll come back to autoencoder. I bet all of you would have heard about recommender systems. The computational model underlying a recommender system are these sparse high-dimensional matrices, right? So it helps to just think about a really big matrix where the rows are users, the columns are items. There are many variants to this as well. For the purpose of this particular session, let's just say users want to watch movies. And you can also think of them as bipartite graph, where each user is a node, each item is a node, each movie is a node, and users have watched and rated movies, then there's a link. Because we all have limited time in our lives, we can imagine this being quite sparse. The goal of a recommender system is to take, let's say, like these are the watch records of users 837 and said they liked it. And then you want to predict something like this. Hopefully that the user hasn't watched but will like. This has really worked in the past decade or so, actually 15 years, since the next Netflix competition that started in roughly 2007. And the intuition that this really works is it's capturing latent dimensions of similarity of both users and items. But in this particular example, you can imagine, well, these are serious movies with an action crime / adventure theme, and the stuff being recommended are also similarly themed. Right, so how do we mathematically think about movies and their themes or genres? Right, whichever word you prefer to use. And this field was initially called collaborative filtering because what it tries to do is to try and guess what a user will like from what everybody else likes. Right. And it's powered by these large data sets, such as the next Netflix price data set, 100 million ratings with 500,000 users, which is not a lot these days. There's also a movie lens data set. There's big and small version, where the small version is really easy for anyone who wants a taste of recommender system to get started. The earliest collaborative filtering model works by like computing a score. Let me see. So user is denoted as U. So this section is from Murphy's book, chapter 22. All the notations are his. An item I, and say like observed rating, say Y of U and I, and then we want to estimate like an unknown rating, because when the user already watched and rated the video, we don't really care about, like, they won't want to, usually you don't want to recommend them to watch it again. If they want to do so, they can do it by themselves, right? So Y hat are the estimates. So you can see there's lots of unknowns in this large and sparse matrix. The fun and the key problem is to guess these unknown entries. So the way you do this is, if like we had some sort of similarity metric between users U and U prime, we can then use that similarity metric to do a weighted sum of what user U prime has rated the same movie, and then just use that score as the estimate for user U. And this similarity matrix, it can come from Y itself. Like we can basically take the rows of Y and then see what are the intersections, or the, like, barring the unknown entries, what are the let's say Hamming distance or L2 distance of the movies that both users have watched. Or it can have like other information, other user profile information. Things like people's age, gender probably matters in their movie taste. It was already a few years ago when I used the movie Matrix as an example in a class, and then people tell me that, well, look, these are movies my dad watches. And that's when I know, well, okay, demographics have changed. We've been talking about dimensionality reduction, and now it's the time to bring it back, right? So as we said, this Y matrix is one with lots of missing entries that we want to guess. So why do we frame this as a matrix completion problem or matrix factorization problem? So in the literature, you'll find all of these names that refer to recommender systems. So to complete, right, so if we complete this matrix Y, we have a matrix Z. And straightforwardly, we're used to L2 loss functions. So let's say we minimize the like square error between Y and Z. That seemed to be a good idea, or at least not obviously controversial. And the model here is we assume Z is low rank, or it can be decomposed into two other matrices. And drawn graphically, something like this. Let's say we have a long and skinny U matrix and kind of short and fat V matrix, or V transpose. U is like this. So we do a matrix multiply, we get Z. So U and V are both dense. They are not sparse. And Z is dense as well, just in this vanilla formulation. And why is low rank a good idea? And note that let's say we have n users and m movies, big M movies. N and M are pretty big. And usually this, let's say we have K, U and V are like their shared dimension is K. Intuitively, right, okay, so there are several things that supports the reason for having such a model. One is as we saw in PCA, lots of real world data, most of the variance lies in a smaller number of dimensions. So that's one reason to do so. And then in terms of thinking about a particular domain, such as movies, you sort of intuitively think of them as buckets. Even movie filmmakers think of them like that. Like every summer, I have to have an action movie, a horror movie, and a romance movie to satisfy the market demand. So each of these K dimensions ideally correspond to these movie categories. And in order to do prediction for the unknown y, now this is getting really simple, right? I just take the u, so this is u transpose. I take the inner product of this u's U2 vector and the i's item vector. If like this will be essentially YUI. The estimate for YUI is this. I'm just going to write it again. VI. So that's simple, just a bunch of linear algebra. Right. So we've now defined the model, the loss function. The remaining question is to solve it. Right? How do we solve this? If Y was not sparse, then this is familiar, right? So this kind of decomposition is SVD. Now what we're tackling is SVD from incomplete data. So there are two ways to solve this in practice. So if we expand this term, essentially we sum over the UI pairs where essentially Y of U and I are known, are observed. YUI minus U transpose VI, right, squared. So this is essentially the loss function. You can see that it's not convex because I have the product of U and V here, and the big U and V matrix, the U and V vectors are the unknowns being solved. But holding U fixed is quadratic in V, holding V fixed is quadratic in U, so therefore we can do alternating least squared. Right. And this is just one of the many loss functions involving data points. We can do SGD by, mini batching the Y entries or doing stochastic gradient one rating at a time. So here's a question for thinking. What does this particular loss function imply in terms of blockbuster movies and smaller art house movies that are not going to be popular? We know they're not going to be popular. Okay, I am not going to answer that and leave you to ponder it or post something on the chat. You can come back to it after the main content. Right, let me pause and, okay, 氢宇宙, how did they generate the training set? Oh, yeah, you just take a bunch of pictures and put artificial cages on them. Or semi-artificial cages on them, you draw on them. Yes, you can add noise. You can also add artificial occlusions and structures. That's how you train these, what's called in-painting models. Fei Yang asks, can I predict genre from title as well? There are two parts to this answer. In general, you could possibly do that, but I don't imagine it will be super accurate. For the math we're covering on this page, no, it doesn't. It simply works on the rating matrix. It does not care who was the director, who are the actors, what the movie is called, how much money it has earned, and what are its target demographics. It does not care about any of that, for a good reason, actually. So my bragging rights to this particular area is autorec is one of papers that I co-authored, and I have repeatedly observed once you have behavioral signal, any context signal you have is sort of overwhelmed, especially in social media. In movies, I believe the title and general information still carries a significant amount of information, but behavioral signal, if I'm trying to predict behavior, then behavioral signal is usually much stronger. Right. Okay, so here are an example. Here's an example in the Kevin Murphy's book on the on how this works. So this is the Y matrix, and this is the Z matrix. You can see that it captures some latent structures. So yes, so to generate these figures in the book, Kevin Murphy simply used SVD rather than incomplete SVD, and then with 50 latent components, which is a lot. But that's roughly, and you can also visualize, right? So this particular thing is take the, we said that there's this V transpose matrix, right? And then what this picture did is to take the two latent moving factors, meaning there's K factors in total, so this is factor 1, factor 2. So I just chop off all the other dimensions and keep 2 dimensions, and then put all the movies like as points in these 2 dimensions. That's how this plot is generated. And you can see that in this 2 dimensions, these are all really old movies, older for you guys. You can see, right, there's a whole bunch of titles. So there was the comment about predicting genre from titles. So there is some signal here, right? So these are, I would say, like romance or woman-focused movies, it seems like, or at least the main characters are women. And then, right, there's a whole bunch of things about killing and so on. So you can see that the latent dimension has captured some information. Right? All right. So back to autoencoders. Yes, using Kevin Murphy's notation, the model is, well, here's a picture from the autoencoder paper. The input is ratings. The paper tried the item-based, and user-based version item-based works better. So for each, so the data that's vector that feeds into this is basically, let's say, so Y of U and I. So this is the Y matrix. It's item based. So I take a column vector from this and particular item, and then treat it as an input vector. And then I just whack an autoencoder at it. So this is essentially Y. This vector is Y of wildcard I. It's here. It's from here. And then I do a linear transformation using V, and I put it through an activate nonlinear function phi, and then I do another linear transformation using W, and I have a bias term B. That's it. Right, so that's model. And the loss function is nothing but the square loss plus the L2 regularizer. Right, simple enough. Right. And this was done in 2015. And moreover, this is the entire paper, 2 pages. it's right. This effort was spearheaded by Suvash Satin during his PhD, halfway through his PhD here, or actually it's slightly more than halfway. As you can see, this is I would say there are many ways of writing impactful papers. Like this particular paper, I think epitomizes one way. Like basically apply an idea to a new problem, make sure it works, write it up. This was 2 pages in total. So this is the model. This is the loss function. This is the diagram you just saw over here. And here are some performance metrics. So it's a proper academic paper, therefore it investigated what kind of nonlinearity and where should we put it. There was also investigating whether we should take rows or columns of that Y matrix. Yeah, and then benchmark it with the state of the art on the movie lens 1 million, 10 million, and Netflix data set that was still available. There's some sparse matrix factorization approach called Lorna, which is quite cool. And RBM, basically, I think Ruslan way of training autoencoders, which is quite a bit more complex. So Sue actually did this pretty thoroughly. And I'm not exactly sure how I feel about this. It is certainly a nice paper, but this is now my most cited paper. It's right. So which almost says, well, if we right. So the way to generate citations is not necessarily the way to sort of propose new research areas or research problems. If you want to learn what Suvash moved on and did after his PhD, after a career, he did his PhD on recommender systems and after a while joined Twitter engineering. So last year he came back and gave a virtual interview with another of his Twitter colleagues, Xi Yang, who did his PhD in systems here. And they talked about so what it takes to work in Twitter and their journey since PhD, which are before and after PhD. So you can feel free to watch it as like entertainment. So what I also wanted to highlight is, well, Suvash have done lots of other work in his PhD. One of the work just before the AutoRec paper was to essentially use social signals, social network to help recommendation. So one of the hard questions that we're not able to tackle in like a quick overview lecture like this is co-star users are hard, meaning if you just signed up to a platform and the platform have no existing ratings from you. So basically in the Y matrix, this new user, new you, this row is all zeros. You can show that by just doing matrix factorization, you cannot recover anything from this row. This is where additional information will help. So Suvash went and did an internship at Kobo, a Canadian ebook vendor, and from that internship, he actually recovered. So came up with this ingenious approach that requires innovative thinking on matrices. So here's the picture from the paper. Basically, we have training users whom we have information about and the target users. So these are new users that we don't have information about, but we know their Facebook likes. So well, these platforms ask you to link your Facebook profile and then they can gather useful information from you. This is not all the ways they do it, but even for, say, one company that just do one type of linking, it makes a lot of things possible. So you can basically think about, right, so the target users have page likes of dimension P, and the training users also have page likes with dimension P. We do some generalized matrix multiply, and combine it with the training users' interaction with items I, then you can essentially predict the affinity of the new users with a set of items I. Right, simple enough. These are some references about deep autoencoders. We did not cover sparse representation this year. Cross that out. So that's all I need to say today. We covered probabilistic PCA. We reminded you about PCA. We talked about autoencoders and its use in image processing and recommender systems. So, okay, Qinyu is taking a step on the question about loss functions. Suppose for a non-popular movie, there will be many unobserved variables because only a few people watched it. There are less items. Loss function will pay less attention to these non-popular movies. Indeed, that is true. So the question here is because I would say, in a nutshell, this particular loss function is biased towards popular movies, right? Movies that are already popular. Meaning if I have a blockbuster that has had 10 million viewers, then that movie is going to have 10 million entries in this giant sum. But if I have a niche movie that only has 1,000 viewers, then yeah, it only going to have 1,000 entries in here. So what the latent dimensions are going to be overly influenced by the popular blockbuster movies. And this kind of objective, like basically inherent class imbalance. So because it's recommended systems, we don't talk about class imbalance anymore. And also in the last lecture on Monday, we also listed this particular objective function where we sum over all training examples and sum over all output neurons. So those are also going to be dominated by popular classes in the training example. Right, these considerations, I would say, are important. And when you actually train a neural network in a workplace, you need to be aware of these inherent sort of tendencies, because they are not like, it's not like I'm classifying cancer or benign where most people come through a benign, that it's obviously an unbalanced problem. In here, it's not often obvious that it's and rebalancing is, there is no single answer that sort of fits all either. All right, so that's what I have to rant about loss functions. Okay, so we're just over an hour and a half. I'm going to dig up the NLP transfer learning pointer for you guys. And if after that people still don't have questions, we'll wrap for today. Right, universal language models. Yeah, this one. Right, so let's say bye then.